In digital communication system, whenever we try to make a digital information from analog information, what we do, the first step is the sampling. That means we have to make a continuous time signal into discrete time signal. Though sampling will give, or yield of the sampling is a analog signal, but it is a discrete in nature. Now sampling must be done subject to certain condition. That means if we try to discretize a signal, it must obey some rule, and that rule is the sampling theorem. So sampling theorem states that if the highest frequency in the signal spectrum, if the highest frequency in signal spectrum is B, the unit is hertz, the signal can be reconstructed from its samples taken at a rate not less than 2B samples per second. So this is what we call the sampling theorem. That means in order to transmit the information in a continuous time signal, we need only to transmit its samples. So this is the basic objective of the sampling theorem, to produce a discrete signal out of a continuous time signal. To prove this sampling theorem, first we will consider a continuous time signal written as, say, mt. That mt is an arbitrary signal, may be drawn in this way, and its Fourier domain, or rather spectrum, it is also assumed to be arbitrary, say this one. So this is mt and this is m omega. Here we are assuming that this mt is band limited, and band limited to, say, as it is said, B hertz. So we can write m omega equal to 0 for omega is greater than omega m, where omega m equal to 2 pi b. Here mt is the Fourier transform, m omega is the Fourier transform of mt. Now we have to sample this signal with the help of a train of impulses. like this. And sampling, we can assume that sampling is nothing but multiplication of two signals. One is, sorry, this one is delta TS. Train of impulse, delta TS, and MT. The output is the GT is the sample signal. GT is the sample signal. So a continuous time signal MT is we have to convert it into discrete domain. The sampling of MT is done at a rate of, say, Fs hertz. Fs hertz is the sampling frequency. Fs is the sampling frequency. That may be achieved by multiplying MT by an impulse train delta Ts. This one. The impulse train delta Ts consists of unit impulses repeated periodically every Ts seconds. So this one is 0, this one is Ts, 2 Ts, etc. 3 Ts, 4 Ts, etc. And this Fs is equal to 1 by Ts. And the multiplication gives us the sample signal G. This sample signal consists of impulses spread every Ts seconds. So if we multiply these two signals, we should get this type of signal. This is GT. The resulting signal GT can be written as GT equal to MT into delta Ts. Now this delta Ts is a periodic signal, so we can use Fourier series to express this one. 1 by Ts, 1 plus 2 cos omega st plus 2 cos 2 omega st plus so on. Here this omega s, Fs into 2 pi equal to omega s. 2 pi Fs equal to omega s. So GT can be written as 1 by Ts into MT plus 2 MT cos omega st plus 2 MT cos 2 omega st plus so on. Now if you take Fourier transform of this, we should get its spectrum. So that can be written as 1 by Ts into m omega plus m omega minus omega s plus m omega plus omega s plus m omega minus 2 omega s plus m omega plus 2 omega s plus so on. That means the spectrum must consist of the original m omega, the message signal. So if you try to draw the spectrum, it cannot be drawn into the scale with this one. Now we have to make it smaller. So this is m omega, this is m omega, first term. These two terms are basically m omega shifted by omega s. So m omega shifted by omega s, something like this. Similarly, these two terms is the m omega shifted by twice omega s. That means it will be periodic structure. Here we have 2 omega f's. Two omega s. This one. So g omega can be written as 1 by Ts summation n equal to minus infinity to plus infinity m omega minus n omega s. So if we want to reconstruct mt, the original message signal, from gt, we must be able to recover m omega from g omega. Now this is possible if there is no overlap between successive cycles of g omega. So let us go back to the spectrum. So this is the spectrum of g omega. So if we want to get back our original message signal, g omega, we have periodic function like this. So these two periods or successive periods should not overlap. If there is any kind of overlap, then because of this overlap, suppose omega s is lower somewhere here, so this portion will overlap with this portion of the previous period, and under this condition, these two signals, since they are overlapped, we cannot reconstruct the original message signal. And if we see carefully this figure, we can see that the overlap will just start, that means this period and that period will be side by side when omega s is equal to twice omega m. And if omega s is less than twice omega m, then there will be overlap. That means the condition that there will be no overlap is omega s is greater than equal to twice omega m. If it is reverse, then there will be overlap. So from this we can say Fs must be greater than equal to twice B. So this is the basic criteria of the sampling. The sampling frequency must be greater than or equal to the twice the bandwidth of the message signal. Now if we keep Fs exactly equal to twice B, then that particular rate is called Nyquist rate. And under this condition, two successive periods will just touch each other. These two periods will just touch each other. This one is called the Nyquist rate. Now we will consider the reverse process of the sampling, that is called the reconstruction. So the process of reconstructing a continuous time signal mt from its sample is called interpolation. So reconstruction gives us the interpolation formula. The interpolation formula. To construct a signal mt band limited to say B Hz, its samples are passed through an ideal low pass filter of cutoff frequency B Hz. So consider the response of an ideal low pass filter transfer function is like this. We have to pass the original samples through this ideal low pass filter. Its gain is assumed to be Ts. So the reconstruction filter transfer function can be written as h omega equal to Ts rectangular function omega by 4 pi B. The impulse response of this filter Ht, which is equal to the inverse Fourier transform of the transfer function, that can be written as twice B into Ts sinc function 2 pi B T. So impulse response Ht can be drawn in this way. It is the usual sinc function. Now if we assume that sampling is done at Nyquist rate, that is Ts equal to 1 by 2b or 2b into ts equal to 1. Under this condition, ht becomes sinc function of 2 pi b into t. So this is the ht sinc function. And here we are assuming that it is sampled at Nyquist rate. Now ht, if you see this figure, is 0 at these points, and these points are nothing but the Nyquist sampling instants. That means t equal to plus minus n by twice b, except at t equal to 0. That means this sinc function has got a certain finite value only at t equal to 0, and at other sampling intervals it is showing 0. Now when the sample signal g is applied at the input of this filter, the output should be empty. Now each sample in gt being an impulse precludes a sinc function of height equal to the strength of the sample. So addition of sinc pulse produced by all the samples results in empty. For instance, the kth sample of this impulse will be mkts h t minus kts. So the filter output of gt, which is the empty, can be written as summation over k mkts h t minus kts. Putting the value of h from here, you can write summation k mkts sinc 2 pi b into t minus k ts. This is called the interpolation formula. Also that can be written as same expression can be written in this way. So this equation is the interpolation formula. Now we will consider spectral folding or aliasing. If you can remember this spectrum of the sample, say in Fourier domain, so this one is B, and assume that Fs is less than twice B. Under this condition, there will be some kind of spectral overlap. So here you can see there is some overlap. So when a continuous time band limited signal is sampled at a rate lower than Nyquist rate, this one, then the successive cycles of the spectrum of the sample signal GT overlap here with each other. So the signal is undersampled in this case, and some amount of aliasing is produced in this undersampled process. Now, aliasing is the phenomena in which a high frequency component of the signal here takes the identity of the lower frequency components. Means this one is the high frequency part. It is going towards the lower frequency part of the sample signal. So because of the overlap due to aliasing phenomena, it is not possible to recover the original message signal because there is a overlap. So so using a low pass filter, whenever we try to reconstruct, distortion will be there because of this region, because of this overlap region. To recover from this problem, a signal is first passed through a low pass filter. This low pass filter is a special type of low pass filter, blocks all the frequencies which are above B Hz. So this process is called the band limiting of the original message signal. This low pass filter is also called the pre-aliasing filter because it is used to prevent aliasing effect. It is called the pre-aliasing. That means before sampling, we have to pass this signal empty through a special low pass filter so that the tail of this portion is removed. So, and this, if there is no tail, then there will be no aliasing. Now sampling may be of different type. So far we discussed is the sample. Here the sample is done with instantaneous idealized impulse function. So the samples are like this. Something like this. But this type of signal generation is almost impossible. So what we have to do, we can generate the signal of finite width. Now once we have finite width, the sampling becomes two kind. Here with finite width signals, the top of the pulses may be flat. Like this. This is called the flat top sampling. And in another case, the top of the pulse may follow the original signal like this. Within its own time, it will try to follow the original signal like this. So this is called the natural natural sampling. Practically we have this type of sampling, and this one is not possible to achieve, but mathematical analysis of this sample is easier. That is why it is called, this one is called the instantaneous samples. Instantaneous samples. So these are the different type of samples available.